Hello everyone, my name is Giulia Mancini and I'm a PhD student at the University of Nottingham. Today I'm going to show you an analysis of the performance of different sediment transport formulations in the non-hydrostatic XBeach model. First of all, I will start with a general background and then I'm going through the aims and objectives of this study. Then I'm going to describe the model used and then I'm going to show you the numerical results obtained. And finally, I will conclude with some recommendations for future works. So coastal areas are one of the most populated zones in the world, and in particular, 1/3 of the world's ice-free shoreline are sandy. Sandy beaches are very dynamic systems which can either accrete or erode at varying timescales, and also the direct effect of the increasing flood risk due to climate change on coastal erosion is still difficult to predict. In this context, the prediction of a beach profile development with numerical models can provide important information to assess if a shoreline is eroding or accreting. For instance, during storms, breaker bar develops on natural sandy beaches, and these morphological features represent a natural protection for the beach, and also they play a crucial role in the exchange of sediment between the swash and the surf zone. Currently, few existing models are able to fully solve the swash morphodynamics, and so these limits their use in the coastal engineering practice. For instance, the non-hydrostatic XBeach model is an open source model which is able to solve the wave-by-wave flow in the nearshore region up to the shoreline and the intra-wave bed changes. And its morphodynamics response has been extensively validated for gravel beaches, but not yet for sandy beaches. So the general aim of this study is to assess the performance of the non-hydrostatic XBeach in the prediction of the intra-wave sediment transport on sandy beaches. And this aim is achieved by means of three main objectives. The first one is by using the existing sediment transport modeling approach within the non-hydrostatic XBeach. Secondly, by newly implementing a wave-resolving sediment transport formulation in the model. And finally, by testing and comparing the performance of the two approaches with laboratory experiments. So the non-hydrostatic XBeach model is based on the one-layer version of the swash model. So the hydrodynamics governing equations are the one-dimensional nonlinear shallow water equations, including an hydrostatic pressure term to account for the wave dispersion. As I mentioned, the sediment transport in the study is modeled by using two approaches. The first one is the existing sediment transport modeling approach, the non-hydrostatic XBeach, which actually was originally developed and validated for the wave-averaged version of the XBeach model. And the second approach is a newly implemented intra-wave sediment transport formulation. Finally, the bed updating is modeled by using an Exner type equation for the mass conservation. So in the WAST approach, the depth average suspended sediment concentration is computed by using an advection equation where the source and sink terms on the right side are represented by an erosion and deposition rate, which are formulated in terms of the total equilibrium concentration and the settling velocity. The total equilibrium concentration for both bed load and suspended load is formulated using the Van-Ryn-Van-Til expressions, which, as I mentioned, were originally validated for the wave-average version of XBeach. So the main issue related to the use of these formulations when the non-hydrostatic XBeach is applied is that the total equilibrium concentration is formulated in terms of the depth average cross-shore velocity u and the RMS wave orbital velocity URMS. So when the non-hydrostatic version of XBeach is considered is applied, the intra-wave flow is solved by using the extended nonlinear shallow water equations. So the total intra-wave cross-shore velocity is included in the term u. As a consequence, when the WAST approach is used, the URMS term is actually equal to 0. In the second approach considered, the suspended sediment concentration is computed by using the intra-wave sediment transport equation of Pritchard and Dog 2003, where the erosion deposition rates depend on a mobility parameter ME, the total bed shear stress, and the critical and reference shear stresses, which are two arbitrary parameters. And the deposition rate is computed as the product of the settling velocity and the near-bed sediment concentration at reference height above the bed. In this case, bed load transport is computed by using the Meyer-Peter-Muller formulation. This model was first verified against the Zhu and Dodd 2015 semi-analytical solution for an idealized bore generated by a solitary wave. And also it was validated against the laboratory experiments of Yang et al. 2010 for isolated waves, so where swash-swash interactions were not present. So the two approaches were tested and compared by considering the laboratory experiments conducted at the wave flume of the Universitat of Catalunya in Barcelona within the AdLab 4th program. And here the figure shows the experimental domain with the main instruments installed and the location of the upstream boundary used for the numerical simulation. And the experiments consisted in bichromatic wave groups condition simulated over an intermediate sandy beach, so where swash-swash interactions were present. And in particular, two bichromatic wave conditions were simulated with the same energy contact. So a broad-banded wave condition and a narrow-banded wave condition were generated, depending on the degree of bending between the two primary frequency components. Each wave condition started from the same initial bed level, and 8 successive bichromatic wave sequences from segment 1 to segment 8 were generated, in each one of a duration of approximately half an hour. In this study, only the first two segments were simulated because they showed the larger morphological changes compared to the subsequent ones. So here I'm showing the numerical results for the broad-banded wave condition, for the total final bed changes and the total average sediment transport rate over the model domain on the left side. And for the intra-swash dynamics in terms of the time history of the velocity and the depth average suspended concentration on the right side. So according to results, the accuracy in the prediction of the time history of concentration for the two approaches was similar. But however, the newly implemented sediment transport formulations better describes the concentration in the especially close to flow reversal, and they better reproduce the suspension of sediments after the first bar within the group generated by the swash-swash interactions. Indeed, when the worst approach is applied, the concentration drops to zero close to flow reversal, where the velocity is also equal to zero, unlikely not in the observations, which are here marked by the red solid line. So these differences led in turn to differences in the morphodynamics response, especially in the swash zone. So when the intra-swash sediment transport formulations are applied, the deposition in the upper swash zone and the erosion in the lower swash region are well captured. Instead, the deposition in the swash region is significantly underestimated by the worst approach. Both approaches are, however, not able to accurately simulate the process of bar formation in the surf zone, and this is reflected by the modeling of the sediment transport rate. Similarly, for the narrow-banded wave condition, results show that the newly implemented sediment transport formulations better describe the time history of the concentration close to flow reversal, and in turn they better reproduce the erosion deposition pattern in the swash zone compared to the existing approach. However, for the narrow-banded wave condition, the observed bar, is more prominent compared to the previous case, and both approaches are not able to reproduce it accurately. So the exchange of sediments between the swash zone and the surf zones is not well reproduced, and this results in an overall deterioration of the modeling of the sediment transport rate. So to conclude, this study reveals that a wave resolving approach for the sediment transport modeling is necessary to solve the swash morphodynamics with the non-hydrostatic XBeach. In fact, the newly implemented sediment transport formulation better describes the intra-swash sediment dynamics, especially close to flow reversal, and in turn, the newly implemented sediment transport formulation shows a better performance in the prediction of the swash morphodynamics compared to the existing approach. However, both approaches shows limitations in the accuracy of the prediction of the time history of the concentration, as well as in the description of the formation of the bar in the surf zone. Indeed, further important physical processes are necessary to be included in the non-hydrostatic XBeach, such as the wave breaking induced turbulence, phasing effects of velocity in the bottom boundary layer, and also the vertical structure of the concentration and flow in a suitable formulation for the models at end can play a key role in the prediction of the intra-wave sediment transport on sandy beaches. Thank you very much for your attention.